Hello. Good evening, students. I'm Shivan Biradar, a PMRF PhD fellow at Department of Electrical Engineering at IIT Delhi in Control and Automation Department. So I'll be taking your assignment problem class. So again, the second week basically concerns about subspaces, basis, dimensions, cardinality of basis set. How do we construct the basis set? So let us have a look at some of the definitions. So uh, linear combinations. So suppose we have n vectors. So these are my n vectors, v1 to vn, v1 to vn. The linear combination of these vectors can be written as this way. So here x1 to xn belongs to real number, that is x1 to xn are constant. So what are you doing basically here is that I am repeating these things actually. So let us take a, so again like Rm means m dimensional space, n dimensional space. So if I have two-dimensional, sorry, let us say that I'll start with a very basic one, one-dimensional space, then it will be a simple line extending to infinity on both sides, and it will start at 0. So this is R1. So if I have two dimension, then it will be R2. So what will I do for this? I'll add a line which is perpendicular to this line. So this is what my R2 looks like. So this is basically my R2. So with an increase in the dimension, I'll be adding a perpendicular line. So how will R3 look? So R3 will be basically another line which would be perpendicular to this XY plane. So it will be mostly like this on both sides. So this is now your R3. So this is what I'm repeating now. So what is a linear combination in practical sense or in figurative sense? So let us say that x-axis and y-axis. Let us say that I have a vector 0, 1. So and there is a vector 1 subspace. This would be 1, 0. This would be 0, 1. So what will be the linear combination of these two vectors? Let us see that this is v2. This is v1. So I have two vectors v1 and v2. So the linear combination of these two vectors can be written as x1 v1 plus x2 v2. So let us say that x1 equal to 1 and x2 equal to 1. So I will take this vector, which is 1, 1. So in similar fashion, for any value of x1, x2, I'll get the vectors in R2 plane. So this is what the linear combination looks like. So basically, if you have n known vectors, if you take a linear combination of these vectors, you will get another vector v in m dimensional space for this example. So what is linear independence? Let us say that we have n vectors. We have n vectors, and the question is whether these are linearly independent vectors or not. So a very simple way to answer this is to see whether this vector, which is 0, 1 and 1, 0, are these two vectors v1 and v2 linearly independent or not? So what does linearly independent says? So if let us take this example only. Alpha 1 v1 plus alpha 2 v2 equals 0. So if these two vectors v2 and v1 are linearly dependent, then this implies that there exist alpha 1 and alpha 2 which are not equal to 0, which satisfies this relation. So For this example, there is no alpha 1 and alpha 2 will except 0, 0. Like if you have alpha 1 0, alpha 2 0, then obviously this is a trivial solution and this will be 0. So we are not including this type of things. So what we are saying is that for alpha 1 alpha 2 which are not equal to 0, is there any alpha 1 and alpha 2 which are not equal to 0 and is satisfying this type of equation? So for this, for these two vectors, there are no alpha 1 and alpha 2 which will satisfy this equation. So let us consider another vector here. Let us consider another vector here, which is 2 comma 0, and this is my v3, this is my v1, and this is my v2. So let us take the linear combination of v1 and v3. v1 and v3. The linear combination of v1 and v3 will be alpha 1 v1 plus alpha 3 v3 equal to 0. Are these v1 and v3 linearly independent or dependent? So v1 is 1 0, alpha 1 plus alpha 3 is 2 0 is equal to 0. If alpha 1 is equal to 2, then this will be 2 0. Plus if alpha 3 is minus 1, then it will be minus 2 0, which is equal to 0 0. So this is linearly dependent. So what did I learn here? V1 and V3, which are parallel to each other, are linearly dependent, whereas V1 and V3, which are perpendicular to each other, are linearly independent. Same thing. So this is what the linear independence says. So if we extend this notion, so we studied for 2 dimension. If we extend this notion through 3 dimension, we'll get same thing. So if I have three vectors V1, V2, and V3 in R3, so we'll get the linear combination of these three vectors. If there exists alpha 1, alpha 2, alpha 3, which are not equal to 0 and satisfies this equation, then V1, V2, V3 are linearly dependent. So this can be extended to Rn, that is n dimensional space. Linear independence. The linear independence part is over. And we'll see what span is. So again, let us take an example. A very simple example. Let's take this example, which is 1 comma 0. So what if I multiply this vector? Say this is v1 equal to 1 0. If I multiply this vector with 2, then I'll get 2 and 0. So which is this. This is 2 0. If I multiply this vector with 3, I'll get a vector 3 0. If I multiply this vector with minus 3, then I'll get this vector. So let us say that I multiply this with a general constant alpha, which belongs to set of real numbers. So for any alpha, like if I multiply v with any alpha, then I can get all the vectors on this line, x-axis. I can generate all the vectors on this x-axis. So what I say, so if this happens, then I say that this vector v spans x-axis. This vector v now spans x-axis. So this is what spanning is. So if I take another example, I have a 3 dimension space. I have 3 dimension space. This is z-axis, x, y, right? So let us say that I have two vectors. This is my 0, 1, 0, and this is another vector 1, 0, 0, and this is third vector 0, 0, 1. So let us consider only these two vectors, v1 and v2. Or let us say that this is vx, and this is Vy. So I'll take the span of these two vectors. The span of these two vectors Vx and Vy. This means that alpha x Vx plus alpha y Vy. Alpha x and alpha y belongs to the set of real numbers. So if I multiply Vx, this vector Vx by a constant number and multiply Vy by alpha and add these two vectors, then I'll generate a new vector here. I'll generate a new vector here. And let us say that alpha x equal to 1, alpha y is equal to 1. Then I'll get this vector. So for various value of alpha x and alpha y, I'll get various vectors, all the vectors. And one of the important thing here is that I'll get all these vector in xy plane only. I'll get all these vectors in xy plane only. So that's why I say Vx and Vy spans xy plane in R3. Right. I hope you understood the concept of span. So I'll be very brief because I have to solve around 8 to 9 questions. So I hope you know what this means. So again, I'll take a very simple example and tell you what basis is. So let us again take in vectors two-dimensional space. Two-dimensional space. I have 1, 0, 0. So if I take the span of these two vectors, then as you know, I can generate all the vectors in this two-dimensional space. I can generate all the vectors in two-dimensional space. Then, then I can call that this vector and this vector 0, 1 and 1, 0 is the basis of R2. So this is what basis means. So what if you have R3? So if I take this vector, let us say that this is 2, 0, 0, this is x, x, this is y, this is z, x, and this is 0, 3, 0, z axis is 0, 0, 9.5. So using these three vectors, I can span whole R3 here, which means that I can generate any vector in this three-dimensional space. So that's why I call these three vectors as basis of R3. Basis of R3. So what does basis mean? Subspace mean. So let us say that you have a vector space. Let us say that you have a vector space. And your vector space, zero vector is located here. Let us say that you have a subset here. This vector space is named as B and this subspace is named as W. So if this subset W satisfies some property, the first property being that 0 must belong to W, that is 0 vector must belong to W. Then second, it must be closed under addition. This is called addition, closure under addition, and closure under multiplication, scalar multiplication. So if I take any two vectors here, let us say that x and y in this subset, and if I add them, then the sum must always remain in this subset. And let us say that I have a constant alpha belonging to this vector space V. If I multiply alpha with x, then this must again come down to this subset W. Then and 0 here again belongs to this subset W. If these three properties are satisfied, then we say that W is a subspace of vector space. So I think this much is enough. So I'll go on to some important problems here. So this is a problem solving session for week 2, and in week 2, professor has covered some concepts on subspace, span, linear independence, direct sum, and yeah, we will be mostly concerning our problems regarding those topics only. I hope this would help you. So, which of the following sets are subspace of R3? So, I hope you remember the definition of subspace. So, subspace has a zero vector. Addition of any vectors in the subspace must lie in that subspace, and the scalar multiplication of any vectors in the subspace must lie in the subspace itself. So, this is how your subspace must. This is the definition of your subspace. So let us see how we can solve this problem. So this is our first problem. So we take a subset. So we'll start with the subset S. So this subset S contains all the vector x1, x2, x3 which satisfies this property. Remember, this S is a subset now, not a subspace. We have to see whether this subset is a subspace. So this subset S has all the vectors x1, x2, x3, this vector, which satisfies this property. So x1, x2 equal to 0 means that there are two possibilities. Either x1 can be 0 or x2 can be 0. If x1 is 0, then x2 belongs to real number. x2 can be anything in a real number set. If x2 is 0, then x1 can be anything. So we get two vectors here. So either this is the possibility or this can be the possibility. So when x1 is 0, x2 can be anything. This can belong to any real number. When x1 is 8 is a constant, then x2 must be equal to 0. This can be anything in R. So for subspace, we have to first check whether. So let us say that we have two vectors, x and y, the same thing, same vector. So these two vectors are in this x comma y. These vectors lie inside the subset S. So does 0 exist in this span? So okay. So we have two vectors x and y. Let us generate a span of these two vectors. Okay. So span of these two vectors means all possible set of linear combinations of x and y. So does this span all possible linear combination of x and y? So the question here is, does all possible linear combination of vectors x and y contains 0 in that? So obviously the answer would be yes, because if I multiply alpha 1 x plus alpha 2 y, if alpha 1 is 0 and alpha 2 is 0, then it is 0. Yeah. So the 0 exists in this span, right? So this is true. So if I take a scalar multiplication and add these two vectors, then what I'll get is this. So alpha into this x plus y. So I'll get this, and this belongs to R3. Yeah, this belongs to R3. But does this satisfy the properties of R3? But does this vector satisfy does this vector satisfy x1 x2 equal to 0 property? No. So this vector does not belong to the subset S. So this is where we can stop and say that this subset S is not a subspace. So this is not a subspace. So let us go on to the next problem. We see here that again we have a subset S, and this subset S contains the vectors of this form x1, x2, x3. And here it is said that x3 can take only integer values. Only integer values. So let us say that we have a vector x Let us say that we have a vector. Let us say that we have a vector x which belongs to the subset S, and x1 can be anything in real number, x2 can be belongs to the real number set, and whereas x3 by definition belongs to the set of integers. Again, I'll take another vector y in the set. Y1 belongs to y1 can be anything in the set of real numbers, y2 can be anything in the set of real numbers, and again by definition y3 can be anything, any integers in integer set z. So is this subset a subspace? So obviously 0 belongs to this subspace, no doubt about it, because 0 is an integer. So if I add these two, the addition of two integer will always give me an integer. So x plus y would belong to the subset S. But what about this property? The scalar multiplication of this vector x. So alpha can be anything in real number because this is my field. So alpha into x3. So let us say that alpha is 1.1. 1.1 into x3. So this will not belong to the set of integers. So obviously, so this part does not belong to subset S. So again, this set S is not a subspace. This is not a subspace. So let us take another example. So again, I have a subset of vectors x1, x2, x3, and this here x1 and x2 are related using this formula. So simply I can write it like that: x1 is equal to root 3 by 2, root of 3 by 2 x2. If x1 equal to alpha 1, then I can write x. If x2 is equal to alpha 1, then I can write x1 equal to square root of 3 by 2 into alpha 1. So this vector x with this form belongs to the subset S. So I have a vector x here which has the form, which has this form. Let us take another vector y belonging to this subset S. So this y will again have this format, where alpha 2 and alpha 2 belongs to real number and alpha 1 belongs to real. So if I add, so so again, now what we have done is that we have two vectors x and a vector y. So obviously the 0 belongs to the subspace. You can check that. If I add these two vectors, then I'll get this type of form. So again, this belongs to subspace. Right. So again, if I multiply this vector with a scalar, then we'll get the same format, which means that this belongs to subset F, and hence this is a subspace. So I hope you understood what is the meaning of subspace now, and how can we solve solve the problems regarding that. So again, a very simple question: for which of the following sets S? So these are sets S. 3, 7 belong to span of S. So we have to find, does this 3, 7 belong to this set or this set or both? And let's see that how it can be solved intelligently actually. So it can be solved by trial and error method, but what is the definitive way of solving that? That is important. So we'll be looking at a very small matrix method here. That will be easy and very handy. So we have two vectors, 1, 2, and 0, 1, which are in the set S. So we have to see whether 3, 7, the vector 3, 7 belongs to this subset S, this set S. So the question is mathematically formed as that whether the span of these two vectors would be this. That is the set of all linear combination of the vectors. This is the set of all linear combination. Sorry, this is the set of all linear combination of the vectors. Whether 3, 7 belongs to this set. So does there exist an alpha 1 and alpha 2 which gives us this one? So the simple answer here would be to arrange these two vectors in matrix alpha 1, alpha 2, and arrange these two constants as a vector alpha 1 and alpha 2. Now I see that I get a form Ax equal to B, where A is square matrix. Right. So A x equal to B. A is a square matrix and rank of A is equal to 2, which means that this is full row rank or full rank matrix. So I can write it like this. A is big. So X, this is what I said actually. So I'll send this A on this side. So I'll get this. So the A inverse would be this. So if my alpha 1 and alpha 2, if alpha 1 equal to 3 and alpha 2 equal to 1, then then I'll get this this vector. So which means that span of these two vectors contains 3, 7. So again the question would be whether 3, 7 is contained inside the span of this vector and this vector. So again, one. So be careful here. See 1, 2, a vector 1, 2, and 2, 4. So take a careful look at this. If I multiply 2 to this vector, I'll get 2 and 4. Remember, these two vectors are same, which means that this vector and this vector are linearly dependently. So I don't think so. At this point only, you have to say that 3, 7 cannot be inside this. Because 1, 2 would be 1, 2 and 2, 4 are linearly dependent, which means that I can take this out of the scenario. Then I say that 1, 2 would be linearly dependent. There's only one vector in this. So, okay. Let us stop here and move forward. So I'll get this and I can arrange as this. So if I take this, does so the question here is does the inverse exist? So obviously not. No, the inverse does not exist because rank of A is not equal to 2 or the rank is not full rank. So inverse does not exist. So the 3, 7 does not belong to subset. So this is how it is solved. So take a bigger problem than this. 1,000 cross 1,000 matrix, 20,000 cross 20,000 matrix. You have to solve this. So what is my third question? So now, consider the subspace U. So they have said specifically here that U and W are subspace. So remember, this is a very important point. So you have two spaces, U and W, and both of them are subspaces. And you have a vector space. So what you have is that a vector space V, which is equal to R3. And your field is a real number, set of real numbers. So this is your three-dimensional plane, three-dimensional 3D, and this is my field. So now the question is then U union W, union of two subspace is the subspace for which choice of U and W? So remember a very important point that U intersection W is always a subspace if and only if U and W are subspace. So what if U union W? So there is no guarantee that U union W is always a subspace, even if U and W are subspace. So that's why they are asking question for what choice of U and W you would get this as a subspace. So let us look at this problem in more geometric way actually. They'll be more intuitive. So the first question says that U is the set of all set of all vectors of this form x, y, and 0. And there is another subspace W. So U is a subspace and W is also subspace of this form, which means that the vector the vectors in this subspace W looks like this. And the vectors in the subspace U looks like this. So there is a 0 on the z axis or z place. So a careful look at this point would give you a clear picture as to what is happening here. So see, the x and y are only non-zero here, whereas this is totally zero. So what we can see here is that if you make z zero, so u only contains this type of vectors x, y, zero. So which means that z is always zero. So z is a point here, which means that you don't have this now. You don't have this vector. Forget this vector z. Forget this. So you will basically have only this mesh. So this mesh is your xy axis. So this mesh is your xy plane. This mesh is xy plane. So this subspace U is basically xy plane. This subspace U is xy plane in R3. And what is Z? So Z, remember that Z is a subspace here. Okay? So Z is XYZ. Sorry, W is XYZ. Okay. W is XYZ means the XYZ means let us say that X is 1, Y is 1, and Z is 1. 1, 1, 1. So this vector comes out to be something like this. So if I take any vectors, if I take, so we have X, Y, Z which belongs to W. X, Y, Z can take any number, any real number, right? So I can get, according to this, I can get any vector in this three-dimensional space, any vector, right? So this means that U here is a subset of W. So U, which is XY plane, is subset of W. Right? I hope you understood this. So from figure, you see that U is a subset of W. So now we see that zero belongs to U union W. So it's a very easy thing. You see that zero belongs to U union of W, and let us take a vector x, which let us take a vector x from the subspace W and a vector y from subspace W. If I add these two vectors, then I'll get a vector, this type of vector, which belongs to U union W, right? And if I take a scalar multiplied x and add it to y, so x again here is this vector and y again here is this vector, then I'll get this vector, which again belongs to U union W. And hence U union W is a subspace. So for this choice of U and W, you get a subspace. You get a, for this two choices of U and W, and taking a union of these two subspace. Taking union of these two subspace, we get a subspace. So let us take another example. So here U is, so always think geometrically first in linear algebra. Then you'll try to understand the higher dimensional part. So let us take another example where U is a subspace and this looks like this. So this vector 100, 200, 1,00,000 all belongs to this set U, right? So what is happening here is that, so U is basically x-axis. U is basically this x-axis. So U is basically your x-axis only, and Y is basically your this. So consider this subspace which is of this form, which means that 010, 020, 01 crore 0, all of these vectors would lie in this subspace W. And let us say that, so W would be basically this part only. So this is only W. So what would happen if we take the union of U, subspace U, and subspace W? So a very good thing here is that this origin lies in both U and W. So if I take the union of these two subspaces U and W, then I'll get a vector of this form, which would satisfy this one, right? Why? Because if x equal to 0, then y can take any value, which means that if x is equal to 0, then you'll get only 0, y is 0. If y is equal to 0, then you get 0, sorry, x 0, 0, right? So this is your u and this is your w. So, using this mathematical form, you can generate both of these subspaces in general. So as I said, 0 belongs to the union of these two subspaces u and w. So let us take a vector x which belongs to u. Let us take a vector y which belongs to w. Belongs to w. And if I add these two vectors x and y, I'll get this type of vector. So where does this vector x and y lie? So I have x1 and y1. Let us say that x1 is equal to 1 and y1 equal to 1. So I'll get 1, 1, 0. So basically 1, 1, 0 would be in here, somewhere here inside this thing. So this is 1, 1 and this would be 0. This is 1, 1, 0. And remember that this 1, 1, 0 does not belong to the subspace W, and also it does not belong to the subspace U. So the union of these two subspaces is not a subspace. So let us take another example. So U is equal to xy0. So U is the subspace which contains all of the vectors of this form. Right. And W is a subspace which contains all of the vectors of this form. So as I said you, geometrically this would be only z-axis. Yeah. So geometrically looking, your W would be only this z-axis. So W is only your z-axis, whereas U is your xy plane again. So U is your mesh. So U is your mesh. This mesh. Right. So does the union of U and union of W give us a subspace? That's the question. It can be seen that the set U is the whole xy plane, right? We have discussed that, and W is the z-axis only. The union of U and W would be x, y, z. So a very simple thing would be that this is a subspace because zero exists. Zero belongs to U union W, and the addition of uh, any two vectors in this subspace belongs to this subspace. That's why it's the union of these two subspaces is a subspace. So let us jump on to fifth question actually. So this what is the fifth question? So let us consider the vector space. Let us consider the vector space V, which is R3 of R. So this is my three-dimensional plane, and this is my field. U and W are the subspace of V. Then which choices of U and W? Then which choices of U and W? V is the direct sum of U and W. Yeah. So this is an other important concept, direct sum. So what does this direct sum means? Let us see that actually first. And then we'll jump on to see how we know that whether the direct sum of two subspaces actually makes a vector space. So direct sum is actually a binary operation here. So it binary operation on two subspaces. Remember, this is a very important point here. So like addition is a binary operation. So if you apply that addition, you need two numbers, two real numbers. So here the direct sum needs two subspaces. So if you take a direct sum of these two subspaces, you must get a vector space. That is what we'll see in the direct sum. Yeah. So what is the direct sum? So let us consider a vector space V. We'll start with the vector space V. And this vector space V has two subspaces U and W. Two subspaces U and W. So, so we say that V is the direct sum of these two subspaces. Remember that V is your vector space. And we say that V, the vector space, is the direct sum. Remember, see there's a word sum here. So don't forget this. So V is a direct sum. We see that V is the direct sum of U and W. V is the direct sum of U and W, which is depicted like this. And let us say that now the important point here is that let us say that I have a vector V in a vector space V. I can if no if V is the direct sum of two subspaces U and W, then this vector V in this vector space V can be expressed as summation of two vectors U1 and W1. So let us say that I have a vector subspace here. I have a subspace here. I have a subspace here, U and W. Okay. I'll take a vector V. So if I can express V as a sum of two vectors, say U1 plus W1, where U1 belongs to this subspace U and W1 belongs to this subspace W1. And this can be done uniquely, and this must be done uniquely. And another important property is that zero, zero must belong to the intersection of these two subspaces, which means that there is a small intersection. There is a small part here, and zero exists in this intersection of U and W. If these two properties are satisfied, then we say that direct sum of U, direct sum of U, and the direct sum of W gives us vector space V. So if this is true, then we say that V is the direct sum of subspace U and W. So I hope you understood this. So very simply thinking. So if I take a vector in vector space V, and if so, I'll start with saying that zero must exist in the intersection of these two subspaces. And if I take a vector V in the vector space V, and I can express this vector V as the summation of U1 and W1, where U1 belongs to the subspace U and W1 belongs to subspace W. And if this can be done uniquely, if this relation is unique, then we say that V is the direct sum of U and W. So remember, this is a very important point. I hope you understood the meaning of uh, direct sum here. So we have a vector space V R3. R, this is my field of real numbers, and this is my three-dimensional plane. So V and U and W are both subspaces of vector space V. So by problem, so the first part says that U is an XY plane and W is a YZ plane. U is an XY plane. U is an XY plane. U is an XY plane and W is a YZ plane. So now I have to show whether this vector space V, which is equal to R3 on field R, is the direct sum of these two subspaces U and W. Which means that if I take the sum of two subspaces U and W, I must get this whole three-dimensional space R3. So we'll use the property of direction. So let us consider a vector v belongs to V, and if I can write V as the addition of two vectors Vxy and Vyz, where Vxy belongs to U and Vyz belongs to W, where U is all xy plane and W is all yz plane. So Vxy will look like this and Vyz will look like this. If I add these two vectors, then I'll get this V. And this operation, this binary operation, uniquely gives us this vector x, y, z. And 0 belongs to the intersection of xy plane and yz. So basically, we can say that the direct sum of u and w gives us the vector space V. I hope now you understood that part. So now moving on to see the sixth question. So the question here is, which of the following subsets S of R3 are linearly independent? So the question here is whether the set S contains linearly independent vectors. So set S has 1 to 1, minus 1, 1, 0, 5, minus 1, 2. So no, you can solve this using you can solve this using trial and error method. But no, it might take you the whole day here. So you'll have a simple thing. It's very easy actually. So I have this set S which has three vectors. I'll form a matrix using these vectors. I'll place all these vectors as a column vector. I'll check the rank. If rank is 3, then that means that we have three linearly independent vectors here. So if you check the rank, I'll get 3, which means that this is linearly independent set. So now the next question, again I'll do the same thing. I will form a matrix out of this and then I'll check the rank. If the rank is full rank, then I'll say that these are three linearly independent vectors. Yeah. The question seventh is actually important. So the question seventh says is that which of the following subset S of P are linearly independent, where P denotes the set of all polynomials with real coefficients. So I have a set of polynomials, and so yes, I have the set of polynomials. I take a small set S, which is this. So now I have to see that this S is yeah, this is the set of polynomials, and there is set S. So how can we say that this set S is linearly independent? So again, the definition of linearly independence or linearly independentness does not change here. So alpha 1 into f1, where f1 is a polynomial, alpha 2 into f2, f2 is a polynomial, plus let us say that we have n polynomials, alpha n into fn is equal to 0. So the question here is that, so sorry, if for non-zero value, let us say that alpha, okay. So again, the same notion here. That is, for non, if this is true for non-zero value of alpha 1 to alpha n, then we say that f1, f2, fn is linearly dependent, and alpha I belongs to the set of real numbers here. For all I equal to 1 to n. So alpha must belong to the real numbers. Remember this. So question number 7. We jump on to question number 7 because we don't have time here now. So we have this set S. The same question. Whether they they said S is linearly independent. Yeah. So I have three polynomials x plus x1, x plus x square, x minus x square, and 3x. So if I take the linear combination of these four polynomials, alpha 1 1 into alpha 2 into x plus x square, alpha 3 into x minus x square, and alpha 4 into 3x, does there exist some non-zero alphas which satisfies this equation? So if that is true, then we say that these polynomials are linearly dependent. So if I take alpha 1 as x, which is actually not, we cannot do this, but if I take alpha 1 equal to x, alpha 2 equal to 1, alpha 3 equal to 1, and alpha 4 equal to minus 1, then we say that S is, then you'll get 0 here. But we are not allowed to do this. We are not allowed to do this. We have to take a constant, so which means that we have to take some number in real number set. Take any number, no, try everything, you'll not get 0. So which means that this is linearly independent. So I'll give a very beautiful method to check, as done in the set of real numbers. No, if you set of vectors, if you have 1 0 0 0 1 0, you'll form a matrix, then you'll check a rank, and then you'll say that it's linearly independent. So how can we generalize that result into the set of polynomials? That's a very beautiful result given by Wronskian. So uh, out of this polynomial, we'll construct a Wronskian matrix. Then we'll take a determinant of that Wronskian matrix to check whether this polynomial are independent or not. So that is another beautiful method here. So question number 8 says that we have a vector space V. So this vector space V contains all the set of functions from R to R, and let us take three functions: f of t which is equal to sine t, g of t which is equal to e of t, h of t equal to t square. So the question here is that whether these polynomials are independent or not. So let us take an intelligent root now and define how it can be checked directly. So here I'll be constructing a Wronskian matrix. So let us consider n polynomials f1 to fn, and these are real functions, real polynomials, and they must have n minus 1 derivatives as well. And if these functions are valid on some interval, so these n polynomials or these n real functions, say these n real functions are true on these interval only, then I'll form a Wronskian matrix. So the Wronskian matrix looks like this. So this is what my Wronskian matrix is. So I'll arrange all the n polynomials in my row, f1, f2, fn. I'll arrange all of these polynomials in this row. Then I'll take one derivative, first derivative here. Right. So I'll d by dx. Then again I'll take d by dx. I'll take n minus 1 derivatives like this to construct an n cross n matrix. So basically I have n polynomials, arrange them in row, and take n minus 1 derivatives and then arrange them in rows. In this fashion, we say this matrix as a Wronskian matrix. And if I take the determinant of this matrix, this determinant of the matrix would give us a very important results concerning the linear dependence of the polynomials or real functions. So now this whole part, this whole part, this whole part, this whole part is called the Wronskian, or the Wronskian of this real function f1 to fn. And now the theorem says that if Wronskian of the real functions in x is not equal to 0, remember that we are taking a determinant here, determinant of this matrix. So determinant of this matrix of polynomials would again be a polynomial. So if that is not equal to 0 for any x in this interval ab, then f1 to fn are independent. So the first thing you have to do is to first form a matrix, then take a determinant, and the determinant of that matrix polynomial or the matrix of real functions. The determinant of the matrix of real function would be a real function, and if that real function is not equal to 0 for any x in this interval, then we say that these polynomials n real functions or polynomials are linearly independent. And further, if there exists one point, x naught, which belongs to this interval, and at that interval that Wronskian is equal to 0, then we say that these all n vectors are linearly dependent. So I think this is a very important result, and you must remember this. This comes handy in many important applications in future also. So I'll construct a Wronskian matrix first. So this is my Wronskian matrix. Then I'll take the determinant of this Wronskian matrix, and this whole setup is called the Wronskian. Wronskian. So if I take the determinant of this, then I'll get this whole part. And the argument t here belongs to the whole real line. And this is not true. Sorry, this is not 0. This is not equal to 0. This is not equal to 0 at any value of t. At any value of t. You can check it. And hence we say that sine t, e raised to t, and t square are linearly independent. This is a very important result. And finally, we have reached on the last question now. So in a vector space V, so sorry, this is ninth question. Vector space V. So span of V1 to Vn. The span of V1 to Vn is a vector V. And if we form another set wherein we add this vector V, the question is whether this set is linearly dependent. Obviously, this is linearly dependent because V is a linear combination of these n vectors. Yeah. So consider the given set S and assess these vectors. What is the cardinality of the largest linearly independent subset S? Yeah. So this is actually a very good question, wherein we'll again invoke some very pretty results from row reduced echelon form. So what I'll do is that I have set S which has some vectors, 4 vectors, and very carefully looking at these vectors, we see that A minus B would give us C. So obviously there is some dependence here. We have to find out what is the dependence. So we have to see, we'll form this and see whether there exists some non-zero alpha for which this whole equation is true. So we'll do that very intelligently. I'll form a matrix out of these vectors. I'll put in these I will put in these vectors in this matrix. I'll row reduce them to get this matrix. And these are my pivot variables. Sorry, these are my pivot positions. This is a very important concept. These are my pivot position. And corresponding to this pivot position, I'll select so this pivot position is first. This pivot position is second. This pivot position is third pivot position. So according to the position of these pivots, I'll select the columns my in my first matrix. So this is my first column, this is my second column, and this is my fourth column. Sorry. So this is my fourth. Yeah, this is my fourth pivot. So 1, 2, and 4 are my pivots, which means that these 3 vectors, first vector, second vector, and fourth vector are linearly independent. If you this vector, so this vector is the linear combination of these vectors, linear combination of these 3 vectors. So remember this result. First form a matrix, then row reduce it, then check the positions of your pivot pivot position. Then check the pivot position, and corresponding to the pivot position, choose the column vectors. Those column vectors would be your linearly independent vectors. So these three are your linearly independent vectors. So the cardinality of your largest independent set would be three. So this was week 2 of problem solving. And I think I must close here now. Thank you. Enjoy your day.